Now let's work on an example about the ridge regression, right? So let's try to do this particular formula. And in this formula, we have a weight matrix, right? But we're going to treat every training data with equal weight. So this weight matrix is the weight matrix becomes an identity matrix. So it doesn't actually have any effect. So we can treat it as phi transpose times phi plus lambda multiplied with a identity matrix, and then the whole thing takes the inverse, and then phi transpose W is identity, right? So ignore it, and then times the F vector, right? So let's try this ridge regression. But now let's switch to a different basis function. We're gonna use this kernel function with this Gaussian kernel functions, right? So basically the kernel functions are the Gaussians centered around all the locations of the training data, and with a fixed width given by h, right? So if we have 50 training data examples, then we're supposed to have 50 kernel functions, right? So in this case, phi, the design matrix is going to have how many points? How many rows? It's going to have 50 rows, right? And then 50 columns also. So because the number of bases b is the same as the number of training data. But let's keep using our previous fake data, right? Fake training data, and then import matplotlib.py as plot, right? And then again, let's generate the fake data. Generate fake training data. Right? Again, we are going to use 50 points, and then x is going to equal to np.linkspace minus 3 to 3, and then small n, right? That's going to be the locations of our training data, and then pix is going to equal to np.pi times x. And then our label for the training data is going to be np.sin pix divided by pix plus 0.1 times x plus 0.05 times np.random.randn small n, right? And then if we want to make a plot of the training data, plot.plot xf, we're going to use blue circles, right? If we run this code, and we are going to call this function, this exercise E10, right? E10. Save it. So that's going to be our fake training data, right? Yeah, it's got random variations on it, right? So now let's do our training, right? And the training is just constructing this design matrix and then take the inverse, right? We're gonna do a comparison, right? We're gonna do a comparison with the least square regression, right? We're gonna if we do not have this damping component, right? And then we are gonna compare it with the damping component, right? So the first thing we're gonna do is to actually construct the design matrix phi. So the design matrix is supposed to have how many rows? The row number is gonna equal to the number of training data. It's gonna be 50, right? x1 to xn 50, right? And then for this particular kernel function, we are gonna have how many columns? The number of basis function is gonna be equal to the number of training data, right? So it's gonna be 50 by 50. So b is gonna equal to n, right? And then we're gonna need some function called h, right? So let's give it some arbitrary value, say 0.3, right? Later on, this is again a hyperparameter, right? Usually you have to actually choose this hyperparameter through experimentation, right? And if we have time, we are gonna talk about how to do cross-validation. This kind of cross-validation will allow us to choose those hyperparameters in a sensible way. but we are not going to use h directly, right? It's going to be 2 times h squared. So let's call it h. H is going to be 2 times h squared, right? That's going to be the number that we have to stick into the kernel functions. And now let's allocate the memory for phi. Phi np dot zeros. It's going to be n rows and b columns, right? And in this case, b equals to rows, so it's going to be a square matrix. And now let's try to construct each of the different columns inside of this design matrix. So for II in range, how many columns? B columns, right? And then each column is just this exponential or this Gaussian function, right? For each column, it's just this exponential or Gaussian function. So phi, the ith column is going to equal to what? It's going to equal to exp minus x. X is a vector, it's an array, right? It's an array. Subtract. It's for each column, it's going to be it's going to be a Gaussian that's located at a different location of the training data, right? So it's going to be xii, right? And this whole thing has to be squared, right? And then divided by hh, right? And that's going to be our design matrix. It's actually quite simplistic, right? Of course, exp, okay, so it's saying that I have to use the numpy exp function, right? That's going to allow me to take arrays as input, right? Yeah, I think that's our design matrix. So if we want to do a least square, regression, then the expression is quite simple, right? So all we have to do is to get theta hat is going to equal to np dot link alc dot p inverse, right? And then get the phi in there, and then the result is going to dot f, right? Yeah, and that's going to be the least square fit, right? That's going to be the least square fit. Let's give it some. Let's just underscore LS, right? That's the least square fit. But suppose we want to try this ridge regression formula. So how are we going to use it, right? How are we going to use it? Now the formula is slightly more complicated, right? It's not going to be so easy to type. But the inverse that we are going to take is upon this particular matrix, right? So it's going to be lambda times this identity matrix, right? And then add with phi transpose times phi. So we are going to need another hyperparameter. Let's just call it LAM. LAM is the lambda here, right? Let's give some arbitrary value, say 0.1, right? And then theta hat ridge is going to equal to what? It's going to equal to np dot ling alc. So what's going to be the stuff that's inside of the inverse, right? It's going to be phi dot phi. It's a matrix multiplication, right? So it's supposed to be phi transpose dot phi, right? It's supposed to be phi transpose dot phi. But why am I using phi dot phi, right? Because phi is actually a symmetric matrix, right? So how do I know it's a symmetric, right? How do I know? Because this x subtract the xii, right? So if you look at each individual element of the x, right? So it's going to be, suppose I have another loop that goes through every element of the x here, right? Say it's jj, right? So it's xjj subtract xii, right? And this jj is going to be the row index. I is the column index here, right? And that's going to give me the jj's row, i's column of the element, right? But if I switch the two indexes, suppose I switch the role of JJ and II. So now I replace II with JJ, and then the index here, JJ becomes II, right? It's gonna be exactly the same, equal to II subtract JJ. Why? Because you have a square here, right? So it means that phi II JJ actually equals to phi JJ II, right? So that's a symmetric matrix. It's a symmetric matrix. Phi is a symmetric. So the transpose of the symmetric matrix is exactly the matrix itself, right? Um, and that's the reason why we don't really need to do the transpose here, right? So that's gonna give me phi transpose times phi. But we are not done yet. We have to actually add this component, which is actually lambda LAM times this identity matrix. And this identity matrix will have to have the exact same dimension as phi transpose times phi, right? What's going to be the dimension of phi transpose times phi? So phi is a square matrix, right? It's a n by n, right? Phi. So n by n times n by n, that's n by n, right? So it's lambda times the identity matrix np dot eye. That's going to give me the identity matrix. And then what's going to be the dimension of it, right? It's going to be n. Right? That's going to be the dimension of this identity matrix, right? But let me break this line. Let me break this line into like multiple lines, right? Right. Okay. And then the P inverse, the generalized inverse is actually applied onto this particular matrix, right? And then now we have to actually multiply with phi transpose times f, right? But that's going to be a matrix multiplication, so we have to do this dot thing here, right? Dot with what? Dot with phi transpose times f. So phi transpose times f. That's phi transpose is phi, right? So phi dot f, right? And that's going to be theta hat ridge, right? And once we got the theta hat and theta hat LS least square and then theta hat ridge, we're done with our training, right? It's trained with the theta hat, the optimal theta is trained with different algorithms, right? One is with the least square thing, and the other one is with the ridge regression algorithm, right? And then now let's try to actually make some predictions. The prediction code is going to be very similar. Again, we're going to try to come up with predictions for 1,000 locations, right? And then those locations are going to be evenly distributed from -3 to 3 with this many points, right? And then we'll have to come up with this phi matrix, the design matrix for all the prediction locations, right? And the phi is going to have how many? It's going to be how many rows? It's going to be capital N rows and then B columns, right? And then we have to do a loop. No, let's not use phi. Let's use capital P, right? P. It's gonna be what? It's gonna be np.exp, right? So now it's not a small x, it's capital X, right? Subtract capital X, subtract what? So for different basis function, it's just gonna be a different location inside of the training data, right? So it's gonna be small x ii, right? And then this whole thing has to be squared, right? And then divided by h. So is P gonna be a symmetrical matrix? No, it's not gonna be a symmetrical matrix, right? Because the dimension is not gonna be the same anymore. Capital N is not the same as small b. Capital N is 1000, so it's not gonna be a symmetrical matrix. Yeah, and that's gonna be our P. That's gonna be our our phi matrix for making predictions, right? And this phi matrix is gonna be the same, but the prediction value is gonna depend upon what kind of a theta, what kind of optimal theta we're gonna use, right? We have two theta values. One is the least square result, and then the other one is the ridge regression result, right? So we'll have to actually make two predictions. So capital F LS is going to equal to the least square fit is going to equal to capital P dot theta hat LS, right? And then capital F ridge is going to equal to P dot theta hat ridge, right? And then let's just plot them with different colors, right? Capital X, FLS, we're gonna still use green for the least square fit, and then we're gonna use red as the ridge regression fit, right? And then let's run it. Okay, so it looks like you have okay, so we have some kind of overshoot for the for the least square regression, right? But this kind of a overshoot doesn't exist for the predictions made using the ridge regression, right? And if we actually blow up the figure, so let me POT dot y lim is gonna go from say -1 to 2, right? Let me try this y lim and see if it's gonna work. Okay, so it's not taking. Oh, it's not the same syntax, right? Or am I invalid the syntax? Okay. Okay, so now. Okay, so now I can see the figure bit. So, but let me reduce the range. So -0.7 to not 2 maybe, but 1.7, right? Now let me run it again. Yeah, that's a better figure, right? So you can sort of see the results of the fit, right? So for the least square fit, it does look like it was able to go through the line, the prediction line, the green line, was able to actually go through almost every point, or almost every training data, which means the misfit to the training data for the green line is actually very, very small, right? It's not, if it's not perfect, but at least it's smaller than the red curve, right? The red curve doesn't actually go through all the training data point by point, right? It only fits the general trend. It only fits the general trend, right? But the important thing is that the red curve doesn't have those overshoots that's inside of the green curve, right? Those overshoots were created because you don't really have constraints, or you have training data at the locations of the peaks, right? Right. It's a underdetermined problem, right? For at least for the least square fit, right? The locations or the peaks of those overshoots do not have training data to constrain them, right? So the green curve is allowed to do any kind of weird thing between those training data, right? But the red curve doesn't have this kind of overshoot problem. Why? Why is that, right? Because you have one additional constraint. We have one additional constraint, which is imposed by this prior. Do you see what the prior actually is? The prior is actually saying that I want the theta hat, I want my optimal theta to be as close to 0 as possible, right? Because theta j is going to be, so the probability for the prior is going to be high when theta j is close to 0, right? So this prior is saying that I would prefer the theta to be as small as possible. So this kind of constraint does not exist in the least square fit, which does not actually in the least square fit we actually did not use any prior, right? We only actually maximized the likelihood. We did not even consider the prior, right? There's no prior constraint about the theta. But here we have a constraint in the ridge regression. We want our theta to be as close to 0 as possible. Right. At the same time, we want to fit the training data. And what I was saying that the result of this fit is going to depend upon two hyperparameters now, right? One is the width of the Gaussian, that's the kernel functions, and the other one is the lambda, right? So now we have two hyperparameters now. So exactly how do we want to choose them, right? But what's going to be the effect of changing those hyperparameters, right? So here h equals to 0.3, right? Suppose I change it to like 0.01. I make my kernel functions to be extremely narrow, very narrow Gaussians, right? So in your head you can imagine the Gaussians are just going to be like a spike. Right, each Gaussian is just going to be like a spike, and each spike is located at the location of one of those training data. Right. Then what's going to happen? Right. Let's run it, and then what's going to happen? You're going to get this kind of thing. Right. That's exactly a lots of spikes. Right. Lots of spikes. But your prediction is going to lose this kind of a smoothness, right? Even though you can fit the data perfectly, but your model or your prediction is gonna lose this kind of smoothness. It doesn't have any smoothness, right? You are purely just fitting the data. So at this point, if I increase my lambda, see what's gonna be the result, right? Increase it by 10. If I increase my lambda, you have some smoothness, right? But you are sacrificing the fit to the data. The reason I'm saying you have some smoothness is because it's not reaching the peak, right? Of course, you're allowed to actually make lambda even bigger. In that case, okay, so 100 is kind of too big, right? 100 is too big. So, but it's still going to be very narrow, right? But if I increase it a little bit, then it looks like the least square fit is able to actually go through all the data points, right? But it's not as smooth as the ridge regression results. But in this case, the ridge regression result seems to be too smooth now because it's actually not fitting the data at all, right? So which means the lambda is too big. Let's reduce lambda, right? Now lambda becomes smaller, right? The fit to the data becomes better, right? The fit to the data becomes better, and then the red curve is still smoother than the green curve, right? So now let's reduce it to like 0.1, right? So now it looks like it's the lambda is fitting the data pretty well, right? And then it's still smoother than the green curve, even though it's actually fitting the wiggles here. These wiggles might be, those small wiggles is supposed to be noise, right? Right. So you could actually increase it slightly, right? But is there any kind of a systematic way for us to actually choose those hyperparameters, right? Is there any systematic way for us to choose those hyperparameters? Can we select these kind of hyperparameters in a systematic algorithm that does not involve this kind of manual adjustments of the of the values, and then the results are still going to be kind of optimal in a certain kind of sense, right? Um, um, that's one of those questions that we may have to answer. But this is going to be the example for ridge regression and its comparison with the least square regression.